The complete motion of a harmonic oscillator is determined by its initial conditions, which again there are two. So the initial conditions are exactly where this thing is at its initial position and what its initial velocity is at that initial time. So, as long as we know these two quantities, then we know exactly the motion of the harmonic oscillator. Now, one thing we can do is we can always regard this position and this velocity as two separate variables, and then we can write a new way to describe the motion of the harmonic oscillator in terms of its position and its velocity by looking at what's known as a phase diagram. So a phase diagram is we're going to treat separately the position and the velocity. So typically the position is going to go on the horizontal axis and then the velocity will go onto the vertical axis. And then the motion of the harmonic oscillator within this two-dimensional system is going to be described by some path. So let's say my path does something like this, where this path is p, which is a function of both position and the velocity. So every point along this particular path represents the motion of our harmonic oscillator at a given moment in time. So, now, first thing to note is this will always go in the clockwise direction. So the path will always proceed in the clockwise direction no matter where this thing actually starts. So given its initial conditions. So here is assuming that it starts off with velocity at zero position. So this thing is at its equilibrium position, moving, and then it's going to go to maximum displacement, zero velocity, and then keep going this way. Now, another thing to note is, given different initial conditions, this thing is going to have different paths within its trajectory. So basically meaning that this path, this blue one that I drew, will be different for different initial conditions than, say, this one. So, for example, it could start off with maximum distance and then run around and do something like this. So this is a completely different path, which is also a function of x and x dot. However, this one has a different initial conditions. So basically, all these guys collected together gives me a phase portrait when I have all of these different initial conditions taken into account. Now, other things to note is that these different phase or these different paths that it follows for the different initial conditions can never actually cross each other. So for example, I could never have one that, say, starts off here and then goes around and does something like this, right? This is not allowed. And the reason for that is because if this thing had two solutions which had exactly the same variables at two different points, then that means that our solution to our differential equation is not unique, but it has to be unique if I have these particular initial conditions to that. So great. So how do I know that these things make ellipses? Well, again, what we know is that what? Cosine squared, oops, there we go, of omega t plus sine squared of omega t must be equal to 1. And again, using the fact that what? We had x was equal to a times cosine of omega t. And then we have x dot is equal to negative omega a times sine of omega t. This then means that this is the same thing then as x squared divided by the amplitude squared plus y squared, or x dot squared, divided by the amplitude squared times the angular frequency squared is equal to 1. So, or if you want to think about it this way, this is then x squared plus x dot squared over omega squared must be equal to the amplitude squared. So the path and the trajectory that these guys actually follow are then ellipses within inside of this phase diagram. So again, by knowing the phase diagram, then I know exactly the entire history of this harmonic oscillator as it has gone through all of its harmonic oscillations. So another thing we can write here is that what? X dot is equal to what? Dx dt. And we also have that dx dot dt, so this is just the acceleration, is equal to minus omega squared divided by x. Now, if I take these two expressions and I divide them by each other, so this is going to give me a dx dot divided by dx is then going to be equal to minus omega squared x divided by x dot. So this actually constitutes then a first order differential equation, which will allow me then to determine actually what the phase diagram looks like without having to actually know what is x as a function of time independently and x dot as a function of time independently. So for example, if I was working with something kind of more complicated, then it's a lot easier to actually solve this differential equation to then determine exactly what does my, how does the velocity depend on x, for example. So it's a lot easier way to determine what the phase diagram looks like without actually having to solve for the phase, without having to solve for the position and the velocity first as functions of time. So what about the total energy? So, again, using the total energy, what we know from before was, that's what? We can rewrite this in terms of the total energy. So again, using that, the total energy is equal to Ka squared divided by 2. Using that solution, we can rewrite this then as x squared divided by twice the energy, divided by this break constant, plus then the velocity squared divided by twice the energy divided by the mass is equal to 1. So basically, again, if we look at our phase diagram, for each one of those different trajectories, each one of those has a given particular amount of energy. Because again, if I rewrite this as k times x squared plus then m times x dot squared is then equal to twice the amount of energy. So for each one of these different paths within inside of the space, so again, let's say I'm looking at this path, this thing has a given amount of energy, which is determined by, again, pretty much the parameters of this ellipse. So the phase diagrams allow us a way to determine the energy and allow us to look at what's actually happening for these harmonic oscillators. So again, in the case where this thing is undamped, these will always create some sort of closed circles. We'll see cases of this when we actually look at damped harmonic oscillators, where what will happen here is that these actually will end up creating spirals due to the fact that we're losing energy, so the energy is getting smaller over time, so this is actually going to create a spiral. So a nice way to think about harmonic oscillation is in terms of these phase diagrams. Gives us another way to interpret what is actually happening.